Unit 5 is titled Atomic Structure, and in Part 1 we're going to talk about electromagnetic radiation and energy. Electromagnetic radiation is the term that's been given to the wave-like behavior that energy exhibits as it moves through space. Hopefully you've seen something that looks like this before, but as energy is moving through space, say from the sun out to the planets, it moves in a wave. This is a very ugly representation of that wave of energy moving through space. There's all different types of electromagnetic radiation that travels through waves. There's microwaves, radio waves, sunlight is an example of energy that moves as a wave, X-rays. If it gives off any kind of energy, it travels as a wave like this. Each wave has different properties that we'll get into here in a minute. But the basics of these waves, we need to remember two terms, wavelength and frequency. Wavelength is the distance between two peaks in an energy wave. It's given the symbol lambda that looks kind of like this, and it's the length of a wave. That one's pretty easy and self-explanatory. The other term we need to remember is frequency. Frequency is the number of cycles per second, or the amount of peaks that pass a given point per second. It's given the symbol that looks kind of like a V, but kind of not. It's got those parts coming off the side. That's the symbol nu, N-U, and this one was lambda for wavelength. So wavelength, distance between peaks, it's got the symbol lambda, and nu represents frequency, the number of cycles per second or number of peaks that go by a given point per second. All of these waves travel at the same speed in a vacuum, and that speed, the speed of light, is represented with the lowercase c, and the value for it is 3.0 times 10 to the 8th meters per second. So very fast. That's the speed of light in a vacuum. A property of wavelength and frequency, we know that they are inversely related. That means that when one goes up, the other is going to go down. When the wavelength increases, the frequency is going to decrease. The opposite's true. When the frequency increases, that means the wavelengths are getting shorter. And they're related with this equation right here. The speed of light is equal to the wavelength times the frequency. So frequency times wavelength equals the speed of light. If we know one, we can solve for the other. So if we know what the wavelength of a certain wave is, we can use the speed of light to just do some simple algebra to identify what the frequency of that wave is, or we could do it the other way around. Very simple algebra. This is a representation of the electromagnetic spectrum, going from very short wavelength on the left to very long wavelength on the right side. So things like X-rays and gamma rays have very small wavelengths, which means very high frequency, which you can see by looking at the bottom of the chart. Remember, the smaller the wavelength, the higher the frequency. And as the wavelengths get longer, the frequency gets lower. And right in the middle is this tiny little part between ultraviolet and infrared. That's the visible spectrum. That's the colors of the rainbow that we can all see. We can't see outside of the visible spectrum, but there's all sorts of energy going on around us. We just can't see it. Our eyes are only designed to detect wavelengths of light that show up in the 400 to 750 nanometer wavelength range. In 1900, a scientist named Max Planck postulated that energy can only be gained or lost in measurable amounts called quanta. Now, at the time, physicists thought that any amount of energy could be gained or lost. It didn't have to be a set measurable quanta, but Max Planck's experiments proved differently. He came up with an equation that helps us relate frequency and energy. That equation, energy in joules, is equal to h, which is Planck's constant, times the frequency. Planck's constant, h, has a value of 6.63 times 10 to the negative 34th joules times seconds. So using this equation, we can calculate the energy given off by a certain wave of energy. We just have to know its frequency, because Planck's constant is constant. It's on your AP equation sheet. It's easy to multiply these two things together to solve for energy. Quite often we'll only be given the wavelength of, say, light, so we would have to use this equation that we looked at a couple pages ago. We would have to use this equation given a known wavelength to solve for frequency, and then we would plug frequency into this equation to solve for the energy for that wave of light. Since Max Planck proved that energy is only given off in specific measurable amounts, called those quanta, we've actually come up with specific wavelengths assigned to specific energies that are given off by certain atoms. This picture up here is an illustration of how a spectroscope works. A narrow beam of light is split apart with a prism, and it's broken up into all the colors or wavelengths of light that make up this light source. So white light, like sunlight, it's going to show the entire visible spectrum. Now over here, this is a picture of a neon lamp, like a Mazio sign, neon sign. It looks orange, but when we look at it through a spectroscope, we actually see that this neon light is giving off energy at several specific wavelengths. Not just orange, but there's also some blue and green that have shorter wavelengths in there. So all of these energies, each line represents a different energy that's being given off by this neon light. We just have to look at it through a spectroscope to see each different one. So each line represents a different quanta of energy that's being given off, and each quanta of energy has its own separate wavelength of light associated with that energy. Niels Bohr, hope you remember him, he took Planck's work and applied it to his atomic model. He said that electrons can only occupy certain orbits within certain energies. So if this is a hydrogen atom, this is our one proton at the nucleus, and these represent possible orbits for electrons, he said that you can only find electrons on these dotted lines, on these specified energy levels. You're not going to find electrons in between energy levels. He also said that electrons that are in energy levels emit no energy. So if we've got an electron just hanging out in this first energy level, it's not moving, it's not going to be giving off any energy. Same, it could be an electron up here in the third energy level. They're just hanging out, they're not giving off any energy. He also said that energy is emitted in quantities called photons when electrons move down in energy levels. So if this electron right here were to go from the third energy level down to the first, it would give off a specified amount of energy, the difference between this third energy level and the first. That amount of energy would be emitted from the atom. Now, if we had an electron going from the second energy level down to the first, it would give off less energy than this first electron, and it would have its own value for the energy, and it would have a different wavelength of the light associated with it. So atoms emit energy in the form of light when electrons move down in energy level, but for those electrons to move to a higher energy level, they have to absorb the correct amount of energy. So for an electron to go from the first up to the third energy level, it has to absorb a photon with the correct energy. The correct energy would be the same amount that was given off as it went from third to first. For it to go up to the third, it would have to absorb that same amount. For an electron to go from the first to the second, it would have to absorb the same amount of energy that was given off as this second electron moved down to the first energy level. So it's specific energies that are given off as electrons move between specific energy levels. If all the electrons are in the lowest possible state, that means they're all in the lowest energy levels possible. That atom is said to be in the ground state. If even one electron is moved to a higher energy level, that electron is said to be in the excited state. So in the ground state, atoms don't emit any energy. They can absorb that energy to move to the excited state, which has the higher electrons that can then move back down and emit energy. So ground state is lowest possible energy, and even if one electron is moved higher, then that atom is said to be in the excited state. Your question for this section: what is the difference between an excited atom and a ground state atom?